hope you're all having a good time in the session so far. So today we're going to talk to you about Subzero.jl. Subzero.jl, which is a model that we are working on for fast and flexible sea ice physics. I am Skylar, this is Mukund, and we're really excited to share with you today. So to start off with, I want to give you a little bit of background on sort of two ideas of sea ice modeling. And sort of the first one is this general type that's used in global climate models. So that's sort of where we're envisioning the world as a grid scale, and within every grid, we have some sea ice, for example, in the Arctic, but we're envisioning the ice really as one big piece. And then within each grid cell, we're solving a set of equations to tell us the stress, the strain, or for example here, exactly how much ice is in that given area. But when we look at the satellite imagery and we look at some really key areas in the Arctic, that's not what sea ice looks like. So this is the Nares Strait. It's a really critical region for sea ice transport. And as you can see, all the ice in that region is made of lots of little pieces, these individual pieces of ice, and it doesn't look like that big sheet that we're seeing in climate models. So the question is, in these really critical regions, which for some other regions tend to be really key to Arctic melting, how important is this difference in representation for understanding dynamics? And so that's where Subzero comes in. So this is a discrete element model. So basically each individual piece of ice is represented as a polygon, and we model all their individual interactions and are able to have things like breakage and combination of different flows. And so we have a native Julia implementation, and we're going to be talking today about how it's fast, flexible, and coupled. So I feel really lucky to be following both Milan and Naveed because they set me up really well. I don't even have to say why it needs to be fast. As Naveed touched on, a good model is a fast model because we're able to do more science. And so, this model actually started in MATLAB, and this has been a port and an improvement and a Julianization, we might call it, of the model to make it more usable. And so this bottom line, and we can see this is a log scale. We have the MATLAB speed, and then the dashed line is sort of where I was last year at JuliaCon, and then through some extensive work in the geometry ecosystem, since last year we've continued to push the speed up. And we're sort of on a final push of type stabilization to get it even faster. This is not working, right? Is the microphone not working? Okay. Oh, it is? Okay, cool. I think it's going in and out in my ears. Wonderful. And so we're really happy with that and really excited to see where we can continue going. But the other thing, as Milan and Naveed talked about, is really flexibility in Julia. And I was really inspired by both of their models when starting to work on this, especially as I got further into Julia. And so we're going to focus in sort of on a small example of this type of flexibility. And that basically is going to focus on flow scale breakage. And when ice is breaking, this sort of algorithm can change based on regime, or just maybe we're not exactly sure actually what the correct parameterizations are, so we need really easily interchangeable algorithms. But luckily, multiple dispatch is perfect for that. So similar to Subzero and Speedy Weather, we have this setup where we have a simulation object, we have a model that holds everything, but additionally we have sort of these plug-and-play settings that the user can sort of set up a run with for all the different physical properties. So we're going to take a quick look at the fracture settings. And from our experience, setting up settings like this is really nice because it allows grouping of key parameters. So for example, how many time steps are we going to take in between fracture, or how many pieces do we want the flow to fracture into? And that really leads to ease of reuse of these discrete chunks. But in addition to that, we're actually starting to put algorithms into the settings. So for example, at what point exactly do we say a flow breaks? Each user might want to try something different as we try to, for example, match satellite imagery in a given region. And so basically, when two flows hit each other, the stress builds up between them. And the general way then to fracture is to look at, well, where exactly is this stress level on what's called the principal stress space? You can just imagine it's a coordinate system and the stress is a point. And typically we have some type of criteria, and if the stress is in the criteria, we don't fracture. If it's out, we do fracture. And so for example, someone might want a type of criteria that's called a Hibbeler yield curve. And so in this example, the stress is outside and the flow would break. But the cool thing is okay, we're dispatching off of this to say in this example we break, but we can also store the parameters needed for this type of calculation within the Hibbeler yield curve. So if you wanted a different type of breakage, so for example, Moore's cone, where the ice would not break because it's inside, we actually need a lot less parameters for that calculation, so we don't have to store them. So this sort of keeps users from having to find parameters you don't need and stops new users from having to scroll through a large input file of parameterizations where half of them might not even be used in a given simulation, reducing sort of confusion that can arise. And we use this idea in a lot of different places in the code, so not just when it breaks, but actually also the calculations for how we even build up stress in the flows, what type of walls we have on the simulation. And so with this, we hope to give the user, as Naveed and Milan pointed out, a lot of ability to play around with these really interesting dynamics that we don't actually know that much about. But another cool thing, and you can add your own, basically, is what I just said. Who knows what will come next?
Hey everyone. So my name is Mukund, and I've been involved a little bit with the development of Subzero, mostly as a user. And what I'm thinking of using Subzero for is essentially to explore different dynamics of sea ice. And here are some, for example, different mechanisms in which sea ice can break from satellite imagery. And sea ice can break in different ways, depending on the season, for example, the proximity to a coastline, the different types of forcings that are there. And we don't really understand exactly how to parameterize these at the moment. There's a very clear lack of understanding. And so here you can see examples where on the left-hand panel you have a lot of winds, which are creating shear into the sea ice pack and breaking it up in these kind of very linear features, which we call leads. And on the middle panel, you can see that it's a much more open space where collisions might arise between flows, and you can see them in imagery collide and break as a result of that. And on the right-hand panel, you see the effect of ocean turbulence, which is essentially shown by streaks of sea ice that take the shape of eddies. And superimposed onto this, we often have waves that can break the ice. So all of these three, you can imagine, will take different types of parameterizations to capture pretty well. So one of the case studies that I've started working on is the breakage of sea ice due to individual storms. So these storms essentially come up onto the ice and they displace it around, and they can cause breakage through these collision mechanisms, waves, as well as heating, which will make the ice a bit weaker. So in order to understand this coupled problem, we were able to essentially link up our Subzero model with Oceananigans and run some idealized simulations that I'll show here. So here, basically, we have a little patch of the ocean, which is only about 130 meters or so, kilometers or so in each direction. And essentially, the forcing is cyclonic, so it's a little simulated cyclone in a small patch. And we'll see these flows essentially move around in response to that. So you can see that this is a very idealized forcing, which pushes out these flows through something that we call Ekman transport. And you see that as these flows bump against each other, they start to break as well, some of these larger ones. And this is using one of the parameterizations that Skylar was talking about, but we can easily modify this and try to tune it to observations. Another thing that we notice in the simulations is the occurrence of waves in the surface of the ice. And this is something that we expect will also break the sea ice pack. And currently, we don't really have a parameterization for essentially capturing that process, but we're in the process of actually implementing that. So with this, I'll leave it to Skylar.
No, just to conclude, so we're using Subzero to explore these finely grained sea ice dynamics and really focusing on, again, the powers that Julia gives us by being able to make it fast and flexible, and also thanks to the work of Oceananigans coupled. And so we're happy to take any questions. Thank you.
Okay. Oh, I see. Oh, I see so many questions actually. Okay, I can go to the others. Okay. Okay. Yeah.
Thanks for the talk. And my question is, well, I imagine that there is a lot of computational geometry that is involved in the development of this complicated model. So my question is, what do you use? Is it this geometry basics or meshes, or is it something that you developed, and what are your experiences?
Wow, are you a planted question? No. This morning, I actually gave a talk with Anshul and Raphael, and basically, when starting to build this, looking at the geometry ecosystem, we were really looking for something fully native Julia, and so that's sort of that increase in speed I was talking about. We're developing a new package, Geometry Ops, which I implemented the clipping for, and we're working on really improving the speed there, and we've seen a really big boost both in speed and also memory from using it, just in the way we've been able to clean up our workflow through Julia. And it actually uses a lot of really similar ideas with the plug and play algorithm. So not to pitch it too hard, but I guess go catch the talk on YouTube, and we would love any developers if you're interested. And I think that's also another interesting point. That's a really good thing for Subzero, because when Geometry Ops improves, now we get this improvement without us having to continue to put in the work on the earth science side. So I would also make a plug for earth science people to consider contributing to more base packages for the sake of their model as well.
Super, thanks.
Okay, I don't think we have time for any more questions, sadly, but we can proceed for the next talk. Thank you again.